Have you used a PID before but have gotten unideal behavior? Either it takes too long to get to the target or never quite gets exactly there. Maybe it's fast, but it overshoots and has to correct back. You're not alone, and today we'll be discussing how to get rid of all these issues for good. We're Simple Robotics, and we're here to make this simple. If you want your slides control to look like this, make sure to stick around until the end, as all the required concepts will be covered in this video. A PID is a type of controller, meaning it can provide control inputs to devices like motors. It's also a form of closed-loop control, meaning it actively receives feedback and updates its control accordingly. A PID controller takes in an error, usually a distance, and provides a response, usually a power. Most commonly, it's used to set motor powers in response to being a certain distance from the target. For example, slides. Over the course of this video, we will be making a critical assumption. The power provided to a motor is proportional to the force it applies. In reality, it's more complicated than this, but it's true enough for our purposes. A PID uses three components to create the response from the error, and it corresponds to the three letters in the name: proportional, integral, and differential. Each type of response has a tunable weight, and these weights will be labeled with a K. The proportional component provides a response directly based on the error. Most often, the error is a distance, so the further the distance from the target, the larger the proportional response will be. The integral component is based upon the integration of the error over time. Integration essentially means add things up. So when we say integrating error over time, we mean adding up error over time. In this example, the error starts positive, but then goes negative, so the total integral is 0 by the end. Lastly, the differential response is based upon the derivative. The derivative is essentially the current velocity, or speed. So the faster we are approaching the target, the greater the differential response will be. To get the total response, we can then use to drive a motor. We simply need to add these three components together, and voila, we have a PID. It's important to note that with all of these equations, if the error is negative, or decreasing in the case of the differential component, then the result will also be negative. This means that a PID will work in both directions. To understand how these components work together, it's easiest to start by looking at some examples. We'll start by just using a P component and setting the I and D to 0. The proportional response is the main component that provides power towards the target. It tries to simulate how a spring would behave. So the further the system is from the target, the harder it pushes. But this alone will either not reach the target or overshoot and oscillate, as we see here. That's where the D component comes in. The D component simulates drag and opposes the P component to slow it down. Remember that since the D component is larger the greater the speed, the faster the P component tries to move the system, the more the D component opposes it. But if we make the D component too big, it will take too long to reach the target. But if we take some time to tune these two components, we can get a pretty speedy and precise response, as you see here. Lastly, the I component removes any remaining error within the system, giving it that final nudge towards the target. But wait a minute. In this example, the I component is 0, and there isn't even any error remaining. So do we even need an I component? That's a great question, and the answer is no. As you will learn if you study higher level math, specifically differential equations, this equation can be tuned to produce a smooth error versus time graph in a perfect and balanced system. This is a super efficient way to get to a target position from a starting offset, and this is exactly how we want our system to behave. For those curious, this is known as a critically damped system. This equation may look strange at first, but if we take a closer look, all it says is that mass times acceleration, which is force, is equal to some number times distance plus some number times velocity. So this is just a simple PD control loop, no I. This should mean that a PD loop is all we need. There is a key constraint that allows for this PD loop to work, and it's that it relies upon a perfect and balanced system, meaning it ignores things like gravity, friction, and any other influence from the real world. A PID addresses this with the integral component, which essentially says, if I'm not reaching my target, try harder. The vast majority of the time, gravity and friction will be the only two significant external factors in any robotic subsystem, so all we need to do is cancel those out. Going back to our original assumption that force is proportional to power, this simplifies the problem quite a bit. Since gravity and friction are both forces, this means that there is some corresponding power that we can apply to the motor that will be equivalent to them. But there is one key difference between gravity and friction. Gravity will always be in the same direction, but friction will always be in the direction of movement. For this reason, we break this down into two separate components, feed forward and lower limit. Starting with the feed forward component, an easy way to think about it is as if you were trying to lift up a block with your hand. Since the total force is what causes the object to move, to get the object to stand still, you need to apply an equal and opposite force to gravity. To get the block to move up, you need to apply a force greater than gravity, and to get it to move down, you need to apply a force less than gravity. Another way to think about it is by breaking down the force from your hand into two components, the holding force and the moving force. If we then add gravity into the system and then shift around the parentheses, we can see that by adding a holding force to our hand, the force of gravity can be canceled out. This results in only the control force remaining, which we have proven that the PD loop can handle. As for the lower limit, all it does is make sure that the PD loop doesn't get stuck while trying to reach its position. We do this by finding the minimum force required to move the system and make sure the response never drops below that value. Most of the time, feed forward and lower limit values are constants, but there's no reason they can't be functions. If, for example, you have a set of slides that accumulates much more friction the further it extends, your lower limit should probably reflect that. You can use a regression to create a function, also known as a line of best fit. Using these concepts, your feed-forward and lower limit controllers can handle any sort of extra force requirements required to create a perfect and balanced system. The same concept can be used to optimize counter-sprung slides, double reverse four-bars, cantilevered arms, and more. With these components combined, proportional, differential, feed-forward, and lower limit, we have our PDFL control loop. Make sure to hit that subscribe button so you don't miss our upcoming code walkthrough so that you can employ your own PDFL control loop.